Hi, I'm Luís Ferreira and I'm here to present you our team satellite, Moonllite. Moonllite is a nano-satellite designed by 5 students from Instituto Superior Técnico. Its dry weight is 6 kilograms and its size is 18U standard. The satellite's mission is to photograph the moon permanent shadowed craters in search of water ice. In order to have a productive work method, each team member is in charge of a specific part of the satellite. I'm the system engineer and team leader for Moonllite. Francisco Enguite is the communication engineer, Beatriz Alves the attitude and orbits engineer, João Caldeira the electrical engineer, and Ricardo Santana is the structure and thermal engineer. Frequent meetings occurred in order to maintain track of everyone's work so that weekly deadlines could be met. These meetings were based on a concurrent engineer style and each member presented status updates while the other members would ask questions if further explanation was needed. Our satellite will start its mission at an altitude of 300 kilometers, increasing the eccentricity of the orbit each time it passes the perigee by applying an impulse to the satellite. This shall be done 41 times until the CubeSat reaches the Moon after 16.5 days. Data will be collected during the flyby and then transmitted to the ground station on the Earth.
Hello, I'm Beatriz Alves and I'm in charge of the mission analysis, propulsion and attitude control and determination. Starting in a circular parking orbit with 6,671 kilometers and a 4.7 degrees inclination, our mission consists of a series of 41 impulses all performed at the same point. This coincidence of the burning points will generate elliptical orbits with sequentially bigger eccentricity while maintaining the initial inclination and perigee. This process will culminate in an elliptical operating orbit of high eccentricity. Simulations using the General Mission Analysis tool show that the operating orbit will achieve a periselenium of 1,832.5 kilometers, corresponding to a 94.5 kilometers of altitude. To perform all these impulses, we have opted for liquid monopropellant propulsion, more specifically hydrazine, due to its high thrust, relatively high specific impulse performance that allows for smaller burner times and hence higher precision. The attitude of the satellite can be perturbed by three main sources: gravity gradient torque, caused by the gravitational field of the celestial bodies such as Earth and the Moon. Magnetic torque, due to the interaction between Earth's magnetic field and the residual magnetic dipole of the satellite. And solar pressure radiation, caused by solar radiation. In order to determine the satellite's attitude with relative precision and independently of the environment conditions, sun sensors and gyroscopes will be required. The necessary corrections will be performed by a set of 3 reaction wheels.
Hi, my name is João Caldeira and I'm gonna talk about the electrical power system of our satellite. The electrical power system is responsible of generating, storing and distributing the power necessary in the spacecraft. This subsystem is composed by a power source to collect energy from the sun and by a battery to store that energy. Once the energy is collected, it must be provided to each subsystem. In order to size each component, our first step was calculate a power budget of the total system. With that in mind and knowing the length of the period that the satellite is in eclipse and in daylight, now we have to choose the type of power distribution. Our choice was direct energy transfer. With all that information, we can determine the power that the solar array must provide during daylight. There are many types of cells for solar panels, differentiated by efficiency, degradation coefficients, and prices. Despite of the low efficiency, our choice was the silicon ones, that have an achieved efficiency of 14.8%. Now we are able to calculate the power production capability of the manufacturing solar array in the beginning of life and then in the end of life. With all these values, now we can know the total solar array area required to support spacecraft power requirements, and it has a value of 0.48 square meters. This solar array sizing is highly affected by the angle between the vector normal to the surface of the array and the sunline, because it is always changing. Next step was about energy storage. These components represent the heaviest parts of any spacecraft, but that can be minimized by using lithium-ion batteries. The main parameters that had to be taken in account was depth of discharge, temperature range, maximum load current, and charge/discharge times. Last but not least, power distribution designs depend on source characteristics, load requirements, and subsystem function. We have to focus on keeping power losses and mass at a
For our mission, we can consider three different operation modes: the orbit mode, flyby mode, and safe mode. The orbit mode is used from the initial orbit until the satellite reaches the moon. The payload is off, but all the other subsystems are used in this mode, so it's possible to have a correct pointing of the antenna towards the ground station, a correct point when using the thrusters, and a status update of the satellite. The flyby mode is used while the flyby is being performed. Correct attitude control is needed, and satellite payload must be active so the mission goal can be achieved. The safe mode is not yet completely defined, but is used if something went wrong and not expected, and is used during the mission while the satellite tries to return to its normal operation mode.
For our structural analysis, we have considered the launching process as the most critical time of the mission. To make the calculates easier, we have approached our 18U satellite to a hollow cylinder with uniform thickness. We have computed the axial and lateral forces our satellite will be exposed to at the launch. Based on that, we were able to compute the equivalent weight at this stage of the mission. With this information, we determined the maximum amount of stress our CubeSat will have to support. Multiplying these values by a 1.1 or 1.25 factor, we can compare it to the hidden ultimate strength of different materials. To finish, we calculated the structure natural frequencies that must be larger than the launcher frequencies. At this stage, we choose aluminum as our main structure material. To the thermal analysis, we computed the range of temperatures our satellite will be exposed to. There are three different contributions. The first one, the radiation absorption by the structural surface. The radiation comes from three different sources: directly from the Sun, from the Earth albedo, and from the infrared emissions by Earth. The last one has been calculated considering Earth as a black body. To the maximum amount of temperature, we considered the diagonal section of our solid as the area of incidence, and the launching stage near to Earth. To the minimum temperature, the basis, and the flyby over the moon. The second and third contributions are the dissipated heat by all the subsystems and the emissions of the satellite as a black body too. With the emissivity and absorptivity of aluminium, we computed a range from 32 to 75 degrees Celsius. So we decided to coat it with a bright aluminium paint and obtained a range from minus 43 to 3 degrees Celsius. Because the most sensible components are on the interior and most exposed to the dissipation of heat, they will stable at higher temperature that allows them to stay operational throughout the mission.
Hello, my name is Francisco Enguita and I'm the communications engineer for Team Moonllite. The main goal of the communications engineer is to manage data transfers between ground station and satellite, as well as controlling the other satellite subsystems through the OBC. The team decided that the top priority was to decrease the satellite size as much as possible in order to reduce costs. All electrical and communication subsystems fit in one unit, which allows plenty of flexibility for the other team engineers. S-band was chosen for both uplink and downlink because it strikes a good balance between data rate, capacity, and having enough transmission power to overcome all the losses, while maintaining a small equipment footprint. we decided that the best option was to have two 1-unit antennas, both used for downlink, one with right-hand polarization and the other with left-hand polarization, in order to minimize interference. This was chosen because it was the best way to obtain the required gain for normal usage, while maintaining the COTS approach. For uplink, the antenna could be one of the DSS 34-meter lineup, because of their good transmission power while supporting S-band. The OBC had to be power efficient while being reliable, so we used the stamp 9G20 that was proven flight heritage while in the MQ2. Because the satellite is only doing one flyby, the 128 megabytes internal memory of the stamp 9G20 is more than enough to store the payload's 10 megabytes photograph, the data coming from the gyroscope and the sun sensors.
I hope you enjoyed this presentation, and we'd like to thank the NanoStar committee for this opportunity to develop knowledge in a very interesting area of study.